In this video, I will explain how to use the fdisk command to create and manage disk partitions on Linux. Disk management involves risks of data loss. If you are learning disk management, you should use a blank hard disk or a virtual machine. I am using a Linux virtual machine to explain this topic. On this virtual machine, I attached 2 additional hard disks to perform disk management related tasks. Let us start this virtual machine. The fdisk command works similarly on all Linux distributions. You can use any Linux distribution to learn this command. I am using Red Hat Linux on this virtual machine. Disk management is a privileged task. You cannot use a regular user account for it. Log in from the root account. The fdisk is a command line utility. To use it on a desktop, you need a terminal. Open a terminal. The fdisk command needs a disk name as an argument. To know the name of all attached hard disks, you can run the lsblk command. It prints a list of all connected hard disks. It also prints partition information. For example, these disks do not contain any partitions. We can use any of these to practice the fdisk command. The fdisk command needs the absolute path of the disk. Linux keeps all disks in the /dev directory. If we use this directory name before the disk name, we get the absolute path of the disk. For example, if we want to use this disk for practice, we will specify its full path as an argument. This command starts the fdisk utility. The fdisk utility controls the command prompt until we exit it. It uses letters as commands. For example, to print the current partition information, we use the p command. It interrupts the letter p as the print command. As we can see here, currently it has no partitions. To create a new partition, we use the n command. It creates only MBR partitions. Before we create MBR partitions, let's understand what MBR is. MBR is a classical way to store a bootloader program and partition information. It reserves the first 512 bytes of the storage device to save this information. Only BIOS-based systems use it. UEFI-based systems do not use it. They use GPT to store partition information and a bootloader program. MBR is non-redundant. It does not replicate the records it contains. If it is corrupt, the system will not boot. It uses a bit complex partitioning scheme. It supports a maximum of 14 partitions. It divides partition into 3 types: primary, extended, and logical. You can create a maximum of 4 primary partitions. If you need more partitions, you need to convert the last primary partition into an extended partition. An extended partition works like a container for logical partitions. You can create a maximum of 11 logical partitions inside the extended partition. An extended partition is not used to store data. It is used to store only logical partitions. Type P to create a primary partition. Type the partition number. The fdisk utility also provides a default value for each argument. To use the default value, we only need to hit the entry key. For example, if we want to start this partition from the first available sector on the disk, we do not need to type anything here. The prompt automatically selects the last available sector for the partition. If we hit the enter key, the prompt uses all available space for this partition. If we want to create more partitions, we need to specify the size of this partition. Instead of sectors, we can use standard units to specify the size. For example, to create a 500 megabytes partition, we will type +500M here. Let us create the second primary partition. Use the default partition number and the first sector value. Specify the size to 500 megabytes. Repeat the same process and create the third primary partition of 1 gigabit. To verify these partitions, we can use the p command. We have created 3 primary partitions. Now if we need only one more partition, we can create another primary partition. But if we need more than one partition, we cannot create primary partitions. In that case, we need to create an extended partition. In the extended partition, we can create up to 11 logical partitions. Let us create an extended partition. Since all logical partitions reside inside the extended partition, use all available space for it. Print the partition information again to verify partitions. Now let us create a logical partition. Since we have utilized all primary partitions, the prompt will automatically start with a logical partition. Select the default partition number and starting sector. Specify the size to 1 gigabyte. Now let us create one more logical partition. This time, use all available space in it. Since we have used all available space on the disk, we cannot create another partition. By default, the fdisk command creates standard Linux partitions. It supports many other partition types as well. To view a complete list of all supported partition types, we can use the L command. The L command lists all supported partition types with their hexacode. To change the partition type, we use the T command. The T command needs two arguments, partition number and hexacode. By default, it changes the type of the last partition. To change the type of any other partition, we need to specify its partition number as an argument. After the partition number, we need to specify the hexacode of the type we want to use. Let us change the type of the last partition to LVM. The fdisk command keeps all changes we make in the RAM until we use the W command. Use the W command to save and apply the changes. The kernel reads the partition information at the boot time. It does not actively monitor this information on the running system. If we make any changes to this information, kernel will learn about the changes at the next boot. If we want to update the kernel about this change without rebooting the system, we need to use the part probe command. This command forces the kernel to reread the partition information. We can use the lsblk command again to verify the new partitions. We can modify partition information in three ways. We can change the partition type, delete an existing partition, and create a new partition. To perform these actions, we need to know the current disk layout. For it, we can use the L option with the fdisk command. With the L option, it prints the same information it prints when we use the P command at the fdisk command prompt. Let us understand this information in detail. These are partitions on this disk. None of these partitions contain a bootloader program. These are the starting sectors of these partitions. The ending sectors of these partitions are listed in this field. These are the sizes of these partitions in sectors. This field lists the same sizes in standard units. These are the types of these partitions in hexacodes. This field lists the partition types in standard text format. If we want to change the type of any of these partitions, we can easily do it by using the T command. For example, let us change the type of this partition. Right now, it is an LVM partition. Let us change it to a standard Linux partition. To change it, we need the hexacode of the Linux partition type. If you do not know the hexacode of the Linux partition type, you can use the L command to list all partition types. As we can see here, the hexacode of the Linux partition type is 83. Let us update the partition type. To verify the new partition type, we can use the print command again. Currently, this disk has no free space. To create a new partition, first, we need to delete an existing partition. Right now, it has two logical partitions. Let us merge them in a single partition. For this, first, we need to delete both logical partitions. To delete a partition, we use the D command. It needs the partition number. By default, it selects the last partition. Since we also want to delete the last partition, we can use the default selection or specify the partition number manually. Repeat the same process to delete the remaining partition. Since logical partitions are created inside the extended partition, fdisk adds their space back to the extended partition. Now let us create a single logical partition. To utilize all available space in it, keep the default selection. To verify the new logical partition, print the partition table again. Save the new disk layout. Run the part probe command again to update the kernel about this change. The fdisk command keeps all changes in memory until we save them. This feature allows us to revert all changes in case something goes wrong. To understand this feature, let us delete partitions. Now suppose we accidentally deleted the partition 3. We need this partition back. In this situation, we can exit without saving the changes. The fdisk will not delete these partitions from the disk until we save the changes. Let us quit the fdisk without saving. We can use the lsblk command to verify the partitions. As we can see here, all partitions are intact. It verifies the fdisk keeps all changes in memory until we save them. Partitions only create boundaries. They do not create indexing and layout. The operating system needs to store data on them. A file system creates the necessary indexing and layout on the partition. Different operating systems use different file systems. Let us understand the file systems Linux uses. Linux uses ext and xfs file systems. ext was the first Linux file system. It was used in early versions of Linux. ext2 was the second generation of the ext file system. It provides very basic features. It was developed in 1980. It was the default file system before RHEL5. ext3 was the third generation of the ext file system. It was the default file system in RHEL5. It was the first file system in the ext series that supports the journaling mechanism. It supports a file up to 2 TB in size. ext4 is the fourth generation of the ext file system. This was the default file system in RHEL6. It uses a series of contiguous physical blocks on the hard disk known as extents. The extents are used to improve the performance of very large files. XFS file system was mainly developed for Unix by Silicon Graphics. Later it was adopted by most Linux distributions including RHEL. It was the default file system in RHEL7. This file system is based on 64-bit extent. It uses journaling for metadata operations. It supports file systems and files of sizes up to 8 exabytes. The only drawback of this system is that it does not support the shrink feature like ext3 and ext4. We use the mkfs command with the T option to create a file system on a partition. This command needs 2 arguments, the file system's name and the partition's path. It creates the specified file system on the specified partition. For example, this command creates an ext3 file system on this partition. This command creates an ext4 file system on this partition. This command creates an XFS file system on this partition. We can create a file system only on the partition that stores data. Since the extended partition does not store data, we cannot create a file system on it. An extended partition stores logical partitions. To store them, it uses a partition table. If we try to create a file system on it, the command finds this partition table and pauses the process. It prompts us to confirm the operation. If we confirm the operation, it creates a file system on the entire extended partition, making the logical partitions inaccessible. You should never do this. We use logical partitions to store data. We can create file systems on them. Let us create a file system on the logical partition. To use a partition, we need to mount it on the Linux file system. So far we haven't mounted the partitions we have created. Since we haven't mounted these partitions, we can use them to save data. To verify it, let us try to create a directory on this partition. Since this partition is not mounted, we cannot create a directory or file on it. To use this partition to save data, we need to mount it on the file system. To mount a partition, we need a mount point. A mount point is an access point of the partition. We use a directory as a mount point. Anything we save in that directory saves in the mounted partition. Let us create 2 directories. We will use these directories to understand the concept of the mount point. We use the mount command to mount a partition. This command needs 2 arguments, the absolute path of the partition we want to mount and the directory on which we want to mount it. This command mounts this partition on this directory. Now, we can use this partition to save data. To verify it, let us create a directory and file. We can use the cat command to create a simple text file. This directory and file will be saved on this partition. To verify it, we can unmount this partition and list this file and directory again. To unmount a partition, we use the umount command. This command needs the mount point's name as an argument. Now let us list this directory again. As we can see here, this directory is empty. The file and directory we created in this directory were actually saved in the partition we mounted on this directory. To verify it, let's mount the partition on the second directory we created for the testing. Now list this directory. This is the file and directory we created for testing. It verifies the data we save in the mount point directory actually saves in the partition that is mounted on that directory. The mount command mounts a partition temporarily. If we want to mount a partition permanently, we need to create an entry in the fstab file. The kernel reads and uses this file at the boot time to mount partitions. If we want to mount a partition permanently, we need to create an entry for that partition in this file. Before we create entries for our partitions, let us take the backup of the current file. A backup copy allows us to restore the system to a working state if we make any mistakes. To mount a partition, we need the absolute path of the partition and a directory. We can use the fdisk command to view the full path of all partitions. To mount these partitions, we need to create directories. We will use these directories to mount these partitions. Now let's open the fstab file and create entries for our partitions. A fstab entry has 6 fields. The first field describes the name of the device or partition we want to mount. Since we are mounting partitions, we will specify the partition name in this field. The second field describes the mount point's name. In this field, we will specify the directory's path we created for this partition. The third field describes the file system this partition has. The fourth field describes the mount options associated with the file system. For practice, you can use the default option here. In the fifth and sixth fields, we use a value of 0. The dump command uses the fifth field to determine whether the mounted device or partition needs to be dumped during the boot time. The fsck command uses the sixth field to determine whether it should check the file system on the mounted partition or device. To enable these options, we need to use a value of 1 in these fields. If we enable these options, it will improve system performance but increase the boot time. On a production system, based on your requirements, you can enable these options. Since we created these partitions only for practice, we do not need to enable these options. Save the file. To test these partitions, we need to restart the system. The kernel uses the fstab file to mount partitions at boot time. If it fails to mount any partition, it halts the boot process. If the system boots normally, it verifies all partitions specified in the fstab file have been mounted successfully. After the login, we can also use the lsblk command to verify the newly created partitions. We created partitions on this disk. We created 3 primaries, 1 extended, and 1 logical partition. These are the primary partitions. This is the extended partition. This is the logical partition. We can access these partitions through these mount points. As you can see here, we did not create a mount point for the extended partition. That is because an extended partition does not store user data. It stores only a partition table that stores information about logical partitions. We need mount points only for the partitions that store user data. We can access a partition through its mount point. For example, we created a file on this partition. Let us list and view that file to verify the partition. We cannot delete a mounted partition. To delete a mounted partition, first, we need to unmount it. We use the umount command to unmount a mounted partition. This command needs the mounted partition's absolute path as an argument. It unmounts the partition in the running session. If we restart the system, the kernel will mount them again. To delete them permanently, we need to remove their entries from the fstab. Open the fstab file. Now remove these entries. If you have taken the backup of this file, you can restore the original file. If you want to delete specific partitions, you need to manually delete their entries from this file. Save the file. The umount command unmounts the partition from the running kernel. The fstab file stores partition entries the kernel uses at the boot time to mount partitions. So far nothing has changed on the disk. To verify it, we can print the partition information. As we can see here, the disk still contains all partitions. To delete these partitions, we need to delete them from the disk as well. To delete a partition, we use the D command. To delete a specific partition, we need to specify the partition number. By default, the prompt automatically selects the last partition. To delete the default selected partition, we only need to confirm the action by pressing the Enter key. Delete all partitions we created on this disk. Now save the new disk layout. Use the part probe command to update the kernel about this change. If you have used the deleted partitions in the current session, the kernel will not accept the change. In that case, you have to restart the system. Restart the system. The kernel reads the fstab file at the boot time to mount partitions. Since we have updated this file, the kernel will not mount the deleted partitions. We can also verify it on the terminal after the login. Open a terminal and run the lsblk command. As we can see here, now this disk has no partitions. All partitions of this disk have gone. That's all for this video. If you have any suggestions, comments, or feedback about this video, please share them in the comment section given below.